So when I was learning about sampling, this was the worldview that I was taught. So on the left side of your screen, you'll see probability samples, and you'll see some nice equations. This is from the Horvitz Thompson 1952 paper, and the idea is that we can do lots of nice math about probability samples. We can provide theoretical guarantees about how accurate estimates are as a function of the sample size and the population. It's just really nice what you can do with probability samples in theory. And then there are non-probability samples which lead to embarrassing estimates. So this, some of you may recognize that President Harry Truman holding up a newspaper reporting his loss in the election, which in fact he actually won. This was an embarrassing failure of surveys. This was in 1948. They had used non-probability techniques, and one of the lessons that people took from this experience was that we should not use non-probability techniques. We should only use probability techniques. So this is the world in, I guess that Horvitz Thompson paper is 1952. That Dewey defeats Truman, 1948. And that was what I was taught in, well, I won't tell you when I learned all this stuff, but pretty recently, not 1952. And so I think really what we have today is a little bit different. What is the true picture of the world is that what we think of as probability samples are not probability samples. So there is probability sampling, the math part of it, and that is all correct and true, and we can prove beautiful theorems about it, and it's lovely. When we try to actually deploy this in the world, that is not what is happening anymore. So telephone surveys now in the US have response rates of around, I think, 6% to 9%, and that's expensive. That's an expensive, high-quality thing. So to have a response rate of, let's say, 10% means you have a non-response rate of 90%. So let me just say that again. You have a non-response rate of 90%, so you are not in this world anymore. That world is gone. That world does not exist. That world only exists in theorem land. And so what people do in practice is they take the data they have and they do weighting to deal with the kinds of problems in the data collection, and that weighting depends on unverifiable assumptions. Then we have non-probability samples, where you have an unknown sampling process with weighting based on non-verifiable assumptions. So what I want to do here is I want to try to blur the line between these things. Like, people often think there's a sharp division between probability samples and non-probability samples. But when you do probability samples and there's a huge rate of non-response, then the sampling process is unknown to you. Let me just give a different way of thinking about this. So often one way to mathematically model sampling with non-response is there's actually two sampling processes. So one is controlled by the researcher. So let's imagine I have a random number generator here, and I randomly pick some of you to be in the sample. That is under my control, and I understand how that happened, and so I can adjust for that in my analysis if every one of you responds. Now, if you all don't respond, let's imagine you have your own random number generator to decide whether to respond or not. That random number generator is outside of my control. Your random number generator is outside of my control, and it's outside of my awareness. Not only can I not control it, I can't see it, I don't know how it works. And so really there is this part of the sampling process that is out of my control and that I can't measure. And that is what happens with probability samples in practice now. That is often a big critique of non-probability samples, is that you don't control the sampling process, but you don't control the sampling process fully either in the probability sampling world. Now, this is not to say that I personally would have equal amounts of confidence from probability or non-probability samples. Like, I think the amount that the sampling process is unknown and the assumptions that you have to make in these settings are different. So I'm not saying that they're equally good, but I'm saying they both involve assumptions, and the question then really becomes which assumptions are we more comfortable with? And that is a much more complicated question than saying always do one or always do the other. Okay, so a probability sample is roughly every unit from a frame population has a known and non-zero probability of inclusion. So a couple key terms here. Frame population is a set of people that are on the sampling frame that you can reach. That is not always the same as the population that you care about. So let's say you want to learn about people in France. And let's say your sampling frame is people on Twitter who have their identification as saying they live in France. So you can, if you want to learn from a frame population about a target population that are not the same, there's going to be some important kinds of extrapolation happening there. So what probability sample, again, means is that every unit on the frame population has a known and non-zero probability of inclusion. The non-zero part is important here. This comes up a lot in digital things where people don't have access to the internet. Those people have zero probability of inclusion, and so you can never learn about them through this kind of mechanism. The second thing is that not all probability samples look like miniature versions of a population. So one of the things we just gave, actually this came up in the questions last time about oversampling, but when people say they want a representative sample, I think they often think they want the sample to look like a mini population. And like that's not necessarily what you want. And often most real complicated, expensive surveys do not have that. They have oversampling, they have other kinds of things to make them more efficient, to make the estimates more precise or to make the cost lower. And so I want to get this out of people's heads that the sample needs to look like the population. If the sample does not look like the population, though, then you have to do some adjustments when you make estimates to do weighting to account for that. So with appropriate weighting, probability samples can yield unbiased estimates of the frame population, not necessarily of the target population. Those are two different things. So to summarize what I think are the main ideas from probability sampling is first, how you collect your data impacts how you make inference. So whenever someone says, here's the data I have, can you analyze it? I say, well, how is this data collected? And that is like understanding the probability that people will be included in the data that you have is key for understanding how you can undo any biases that exist in how those people came in. And the second is you want to focus on properties of estimators, not on properties of samples. Again, people say, I want a representative sample. And I say, well, I don't care if the sample is representative. I want an unbiased estimate. And you'll notice that often we often talk about properties of estimators. This estimator is unbiased. This estimator is consistent. And we're not talking about the sample. We're talking about the estimator. So those are, I guess, two ideas from sampling that I think are important that carry over also to when you're working with a big data source that you don't explicitly sample, but is a sample of something. Okay, so another thing that you see very, very, very often, I guess this is maybe perhaps one of the most important equations in all of sampling. This is sometimes called the Horvitz Thompson estimator or the pi estimator. It's just a weighted average. So basically what you see, let's say I want to estimate the average height of Princeton students. So that's the thing on the left. So we often use the hat to be an estimate and the bar is average. And then we would take the height of everyone in our sample, those would be the yi's, and we would divide them by their probability of inclusion. So I want to talk about the probability of inclusion here. So the probability of inclusion is if we have people who are, let's imagine we just did a simple random sample, everyone is equally likely to be included, then we can just take the average of the people in our sample. But now let's imagine I'm doing this sampling, and imagine that people who sit in the front row are more likely to get sampled than people who sit in the back row. So then I have to take advantage, I have to include that information in my estimator. And so as people are less and less likely to show up in the sample, they have to count for more and more in the estimate, right? So this is why the weighting happens in the denominator. One way to think, the lower your probability of inclusion, the more weight you should get, okay? So inference from probability samples, in theory, you take the data that you have from your respondents and you have known information about the sampling process. So those pi i's. That's probability sampling in theory. Probability sampling in practice, we don't really know people's probability of inclusion because there's non-response. So then what we do is we take the information people give us and then we try to estimate people's probability of inclusion using information about the sampling process. This usually includes auxiliary information about the people and some assumptions. And we'll talk more specifically about that in our activity. You're going to get some practice with this. So you all are going to take a survey, deploy a survey to Mechanical Turk, and then try to use it to make inference about the US population. And so in that process, you might say, well, people on Mechanical Turk are going to be different than people in the US, and that's true. And so you're going to have to do some kind of weighting to deal with that problem, and that involves making some assumptions, and you're going to get some experience doing this. Inference from non-probability samples, again, the same thing. You don't know the probabilities of inclusion, so you estimate them based on auxiliary information and assumptions. So here is one type of, this is just basically a one form of non-probability sampling adjustment model. So basically, I'm just going to skip this because we'll have much more time for this in the activity. It's better for you to just do it yourself than hear me try to describe it. So the key to many of these adjustment methods is to use external information and to make assumptions. So let me explain what kinds of external information you have to use. So imagine that you have a sample of people. Let's imagine you do collect a bunch of data in Germany and 90% of your sample is men. So you might say, that doesn't seem right. Like, I don't think the population of Germany is 90% men. And so you might need to then make some adjustments. But there you've used external information, which is your knowledge about what the gender composition is in Germany, right? And so most of these techniques involve you comparing stuff about your sample to stuff that you know about the population, usually from the government or some kind of national statistical agency. If this external information that you have is not right, or if the assumptions you make to do the kinds of adjustments are wrong, then you can make things worse. But in most situations I've seen, these kinds of adjustments to deal with the sampling process generally make things better, but not perfect. So when Brandon Stewart yesterday was talking about shrinking as much as possible the bias, like that's a good way to think about it. You're not going to eliminate it, but you're going to make it smaller. So let's give an example here where imagine you want to estimate the average height of Princeton students. We can assume that 50% are male and 50% are female. You stand outside of Lewis Library and you recruit 60 Princeton students. 20 of these students are male and their average height is 180 centimeters. 40 are female and their average height is 170 centimeters. So what is your estimate for the average height of Princeton students? So this is the Thinkpairshare. So I want everyone to think about it, then talk to your neighbor, and then we'll come back and have a vote about what your estimate is. Okay? So everyone think for 10 seconds. I've got a clock up there, so I'm going to really do 10 seconds. 10 seconds is a long time. I'll be quiet. Okay, pair. Talk to your neighbor. Talk to your neighbor. Good, okay. Okay. I heard some good discussions. So what I would like to, rather than calling on any one person, what I would like everyone to do is to shout out your answer all together on the count of 3. So I'm going to say 1, 2, 3, go. And when I say go, everyone yell out what you think the answer is. Okay, ready? 1, 2, 3, go. All right, so this is great. This is, I heard all the conversations that I wanted to hear. That's great. So 175, let's walk through a couple. There's 2 main ways that people do it, right? One is the weighted mean. So it sounds like a lot of you did that. So you said, I know that half the population is men and half the population is women. And so what I'm going to do is I'm going to take the best estimate I have for men and multiply that by the size of that group, weight that by the size of that group, and I'm going to take the best estimate I have for women and weight that by the size of that group. So that is a technique called post-ratification, and that's the technique that you all will be using in a more complicated version of this in your activity today. And so I want to emphasize how that's different from just taking the sample mean. So one of the things you could do is you could say, I just want to take the mean of the data that I have. But you all thought the right thing to do was to try to use the external information to correct for the fact that your sample didn't quite look like what you were expecting. Now, how could this go wrong? I heard a couple of examples of that. So one of the things I heard is, well, you're sampling in front of the library. Like, what if people from the basketball team spend more time at the library? For sure, that is not going to be accounted for here. And now, which is also a very important lesson about post-ratification, which is that post-ratification allows you to undo sampling biases related to things that you have measured and that you have the appropriate information to construct the weights about, but not things that you haven't measured. So this is why if you are going to do post-ratification, you have to think about what are the kinds of biases that might exist in the sampling process, and then you have to collect the information that you will need to make those kind of adjustments. Okay? So this is like a mini version of one part of the activity that you'll be doing this afternoon. So now let's see a much more complicated version of that exact same idea. This is a study by Wei Wang and colleagues forecasting elections with non-representative polls. So they took a sample of people who are on the Xbox platform. And so for people who don't play Xbox or don't have a kid that plays Xbox, it's a video game platform. It's really fun. People who are on the Xbox are not a random sample of Americans. So this graph shows a comparison of the demographic characteristics of people they were able to sample from the Xbox compared to people in the voting age population. So it is kind of hard to see all of that here. I want to call your attention to the fact that on the leftmost panel is the sex composition. And so the people on the Xbox are about 90% male, which does not match the voting age population. And they are mostly 18 to 29. That's in the third panel. And again, that does not match the age composition of the US. On other dimensions, though, the population they were able to recruit through the Xbox matches the US population pretty well. But on some it doesn't. So this sample is not a mini version of the US population. However, they were able to collect an enormous amount of data. So they have 350,000 unique respondents and about 750,000 interviews. So this is a case where I am not telling you these numbers just to sound impressive. This actually allows them to do a different kind of adjustment technique. So I want to emphasize this again. You often hear people in computational science say big numbers. I have this many billion tweets or this many trillion tweets or whatever. And I think whenever you hear that, you should ask yourself, does that number actually matter? And sometimes the answer is no. Sometimes the answer is yes. And this is a situation where the answer is yes. And the reason it's important is it allows them to do a better job of adjusting for the sampling process and the non-representativeness, the biases that exist in their sampling process. So the x-axis here is the date. The y-axis here is the estimated support for Obama. The bottom line is what you get if you take the sample average. And the gray, the shaded gray, is what you get if you make a weighted average. So remember, with the weighting, you took the average height of men and the average height of women and then combined it. Here, what they did, instead of splitting the population into two groups, they split it into hundreds or thousands of groups, and then did the exact same thing. And when you split those population into lots of these small groups and combine them just in the way that you did, you're able to take this estimate that bounces around wildly and produce something that is very similar to the actual election result, which is this dashed horizontal line. You can also see the other line there that's labeled pollster.com. That's the average of a large number of telephone surveys. So one of their most surprising results was that the Xbox non-probability sample was able to make more accurate estimates than the telephone survey that was based on probability sampling in practice. Again, if it was probability sampling without all of the problems of the world, then it would work perfectly. But that does not exist. That is not a possible thing that we can do, is perfect probability sampling. If you can do perfect probability sampling, do that. Like, this whole conversation is over. But if you can't, and you probably can't, then you're in this murky world where it really depends on the details. So this is a very exciting result to me, and I think it shows that if we work with non-probability data, we don't have to go back to 1948. It's not always the case that we're going to have a colossal, embarrassing failure. But the techniques that they used here are not the techniques that people used in 1948. A much more complicated way of dealing with the data to make the estimates come out and have good properties. So this is an inspiration for the activity that you'll do later today. This study, they said, we did this on Xbox with an enormous sample. Could we do it on MTurk with a much smaller sample? And that's what you'll get to find out later today. So now I want to just give one also thought about the future and what I think the world is like today and what I think the world will be like in the future. So the x-axis here is cost, the y-axis is error. And so I want to emphasize, actually, even by drawing the axes like this, I've already made an important decision. So first is I've put cost in the picture. And I want to emphasize how important I think that is for us as researchers. So how, like, often we only care about error, minimizing the error, minimizing the error. But again, if we can, that ignores cost, and cost is inherent in how surveys work, right? Like, we could do a whole census. That would be the best, that we should talk to everyone. But we don't, because we say the trade-off between costs and errors is not appropriate. Like, if we talk to 1,000 people, we can get almost as accurate an estimate at substantially cheaper price. Like, baked into the way people do think about surveys is a trade-off between costs and errors. So Bob Groves has this fantastic book called Survey Cost and Survey Errors. And it's all about how we make these trade-offs in all different parts of surveys. But then when people want to introduce non-probability sampling and get potentially higher errors at potentially much lower costs, people say, oh, we shouldn't focus on costs. We can't focus on that. So anyway, cost, very important to consider. So I think right now, what we would like to be is in this bottom corner where we have low error and low cost. Now, I think non-probability samples right now are generally more error and less cost than probability samples in practice, but I do think there is some overlap there. So I would not say that one is always dominant of the other on either of these dimensions. And I think in the future, this is the way things are going to go. So I think we're going to see the trends with probability samples in practice are really, really bad. Non-response rates go up and up and up. Costs go up and up and up. This happens on telephone surveys. It happens on face-to-face surveys. It happens on commercial surveys. It happens on government surveys. The evidence of this is very strong, and the trajectory has been going on for a long, long time. Non-probability sampling, the trajectories are less clear, but even in the short amount of time that I've been watching this field, you've seen a lot of improvements in how a lot of the online panels work. You've seen people developing new techniques for interfacing better with people through digital platforms. So I think increasingly we're going to see lower costs and lower errors for these non-probability samples. So this is sort of the way I think the field will be moving in the future. So to wrap up, samples do not need to look like mini populations. The keys to making good estimates is for the estimation process to account for the sampling process. And that requires you to understand the sampling process. And that's the hard part. There's not a bright line difference between probability sampling in practice and non-probability sampling. And to learn more, these are two books about sampling that I would recommend. The Lore book, I think, is a little bit less technical. The Sarndal book is a little bit more technical, and I think both are really good. Any questions? Yep. Oh, let's start with the live stream.
Got a couple from the live stream here. First from Jorge. For the Xbox paper, did they repeat the survey several times? How did they estimate the percentage points for all those dates?
Yeah, so the survey was running all the time. And they were treating the data. I believe what they did is they treated the data up to that point and made an estimate. And I think they had some kind of weighted average where they counted old data a little bit less than they counted the most recent data. So the survey was running all the time.
And then our second question from Kieran. Is there a level of disproportionality across some categories at which we should be concerned that the categories are poor reflection of that section of the population? So in the Xbox example, maybe we have 10% women that are extremely non-representative of women in the population in terms of attitudes.
That's a great question. So I want to say a couple things about this question. So first, even the categories that we make are not, like we say, are not homogeneous, right? So not all men are the same, not all women are the same, not all white people are the same, not all Hispanics are the same. Everyone's different. And so when we create these categories, there's always an important consideration about whether there's heterogeneity within that category and whether you have the information you need to do post-ratification on that. So maybe that women that play Xbox have different political attitudes than women who don't play Xbox. And so I think it's a good rule of thumb to think if your sample is so very, very different than your population, it's good to wonder, let's say it was 60-40 men and women on the Xbox, then you might say, well, I'm not so worried that those 40% of women are really different than other women. But now let's say it's 95-5. And so then you might say, well, maybe those women are really different. And so I think it is a very good idea to think, as a rule of thumb, if the sample composition is very skewed, we should really think carefully about whether we're adjusting for all the things that we need to be adjusting for. The second thing I want to say is that as people in the group, let's go back to the height example of students at Princeton. Let's imagine there's just one. I think in the sample there was 40 men and 20 women, or maybe it was the other way around. The other way around. So there was 40 women and 20 men. Let's imagine there was only one man. That man would then have a huge impact on the estimates. So that person would get a lot of weight. And that is unstable. And so one of the things you always want to watch out for is if there's a lot of variability in the weights, that's a bad thing. And so there's a great example from the 2016 election. There was one poll that found Trump had very high support among African Americans. And this was because there was one African American man, I believe between 18 and 29 in the Midwest. And he was the only respondent they could get in that category. And so his weight was like 300,000 people. And so from a statistical perspective, we can understand why that is. But then he was unusual. And so that ended up having a big impact on the estimates. So there's a great newspaper article where they found him and talked to him. And so you want to avoid a situation where you have big variation in the weights where one person can be standing in for many, many, many people.
Another one.
Okay. And then we'll do one more, and then we'll go through the room, and then we'll come back.
So from Jorge, again, kind of responding to your comments just now, in the same vein, if the response rates in a certain category, so like males age 45 to 50, high income, et cetera, is very different from another category, then shouldn't the post-stratification estimates be biased, as the weighting does not know which categories are more biased?
No. So if the response rates within the groups do not need to be the same, as long as everyone within, so there's two kinds of variation here. There's many kinds of variation, but there's two I want you to focus on now. One is variation between groups, and one is variation within groups in terms of the probability of response. So if it's the case that all men between 18 and 29 have the same probability of response, and all women between 18 and 29 have the same probability of response, those two do not need to be the same. That's okay. Now, what causes problems is if within a group there's variability in the probability of response, then that can cause problems. So this is the response homogeneity model. I will write down a more formal version of this when I do the introduction to the group activity, because the main part of what you all will be doing is making these groups, producing estimates for them, and then combining them. And so I want you to think carefully about how that can go wrong. So we'll pass the mic. Oh, good. Okay.
Yeah. I wanted to ask if there is some kind of a framework for making these adjustments. For instance, one example is to adjust only in cases where you see the huge difference. And no matter, even if you don't see how men are somehow different from women in this case, in what you're trying to measure, you still adjust for it, for the difference, or you need to have some kind of a theory, what can influence the results, and so these adjustments in this case will be different for different variables. Do you see what I mean? Yeah.
Yep. Okay. So there's a couple good issues in there. So I definitely think you do need a theory to decide what variables you want to try to adjust for. Because you have to have some understanding of the possible biases in the sampling process that you might be trying to undo. So theory is maybe a strong word. I think you have to have some intuition or domain knowledge or some understanding of the population you're working with. The second thing is, might you want to use different adjustment techniques for different outcomes? So in a survey, we often collect many questions, so we often make many estimates from a single survey. It's true that you can do different weighting for different survey questions, and that has to do with for reasons I will show you a little bit later, you might want to do that from a statistical perspective. In practice, I very, very, very rarely see that. I often see people make one response model and they keep that for all of the outcomes. I think that's largely done for practical reasons and also for communication reasons. So if you say, here's the model I used for this question, here's the model I used for this question, it gets very complicated. Okay. Yep.
Okay, so see if I just got this right, because I think my question was answered. So if there's, if your sample is big enough, even if it's non-probability, as long as there's enough people in each bucket, and the probability of selection within that bucket is homogeneous, then post-stratification will give you a reliable estimate. Is that accurate?
That's accurate.
Okay, that's all I need to.
Yep.
So my question is, if we really want to have an unbiased estimator, for example, the Horvitz Thompson estimator usually has a very high variance in practical, and I know there is some other estimates like Hayek estimate, which is a little bit unbiased but have much smaller variance. So maybe I'm thinking if we can just have a go like trying to minimize the mean square error instead of just focused on the bias.
I love this question. You can see me smiling as you're asking it. So this is, I think, a great question. Let me try to provide a little bit of context here. So I think for social scientists, we are often trained that the property that we care about is unbiasedness. And let me just briefly, that means in expectation, it will give you the right answer. Sometimes it can be way too high. Sometimes it can be way too low, but we just want, on average, to give us the right answer. So in data science, that's often less often thought of as a criteria. Often their kind of default criteria is lower mean squared error. So mean squared error is how close is your estimate to the truth. So you could see, like, as social scientists, we often say we want unbiased estimates. And data scientists often say we want estimates that are close to the truth. These are very different starting points, actually. They're both totally reasonable. And so what you often see is that some techniques that might be unbiased might actually give you estimates that tend to give you estimates that are far from the truth if they have high variance. And so there are techniques that allow you to introduce a small amount of bias to decrease the variance a lot. So this kind of bias-variance trade-off shows up a lot. We'll see that also in some of the other days. And I think it's a great question, and I think it depends on how you're going to use the estimates and what community that you're going to be working with. So if you're going to be trying to publish this or not just about publishing, but if you're going to try to communicate this to an audience of survey researchers, they're used to being very concerned about unbiasedness. And so you're going to have to at least be thinking about that and being very explicit about why you're introducing bias and how much the gains you get from that are. If you're going to be communicating with a data science audience, and then they're going to be expecting you to minimize the mean squared error. And so if you care about unbiasedness, you're going to have to really justify that and show you're not losing too much in terms of mean squared error to get that property. So I think it's a great question.
So there's no reason you couldn't use post-stratification with even a profoundly probability sample that had profound non-random non-response, right? And why wouldn't you always try to do that to improve external validity and make the standard errors math more straightforward? Yeah,
so I personally think you should always do post-stratification. But I do want to say that post-stratification requires assumptions, and if those assumptions aren't right, then the adjustments aren't going to do exactly what you think. And so when you said like a profound problem, that made me think, I'm really worried about whether those assumptions are right now. If there's like a really big thing that's happening, if I don't really understand what that thing is, then it'd make it hard for me to adjust for it. So like, if it's a problem that I kind of know about and think I understand, then I feel much more comfortable than if it's like something went totally wrong, I don't understand it, but I'm going to try to adjust for it anyway. I mean, the beauty of probability samples in theory is that we don't have to do that. We don't have to make these assumptions about the population and the response patterns because the randomness takes care of it. Okay, we have one more question from, two more, and then we'll move to the next section.
First from, and I hope I'm pronouncing this correctly, Ikil Tezilani. Can weights compensate for noise in the sample in the case that there's low n for a specific group in the sample?
Yes. So one of the post-stratification is often used as a technique, even in probability samples, to reduce variance. It's like helping you make sure your sample and your population are more in sync.
And then this one from Samira, again, apologizing in advance for mispronunciation. In a setting where there is little information on the population, so data-sparse environments, how do you correct for any biases resulting in the sampling process, so in the absence of reliable population data?
Yep, it's a great question, and the short answer is you can't do it. I mean, post-stratification requires you to have known quantities that you can use for the adjustment. So imagine if you didn't know that Princeton was half female and half male students. What would you do? Can't. It's hard to know. So just as a sidebar, this to me is an argument for why national statistical agencies are very important now, because we have more and more of this kind of ad hoc data collection. And if we have better known quantities that people can use to calibrate against, we can potentially unlock lots of value in all of this data that's being created. But that can only happen if we have these known quantities that we can use for adjustment.